Hi, and welcome to this video. This video is going to be about something called oxidation and reduction. Now, oxidation and reduction refers to then a process involving the transfer of electrons. So if you have a transfer of electrons, then you have to have something that is willing to give electrons or lose electrons, and you have to have something that is willing to gain electrons. And so the process that we're talking about then, in this process, oxidation is the loss of electrons. And reduction is the gain of electrons. And we have a nice mnemonic for this. It's called oil rig. And we can see then oxidation is loss and reduction is gain. Right? So this is for redox reactions. A very basic kind of redox reaction is the following. So let's look at a reaction between sodium solid, which is a metal, plus chlorine gas to form sodium chloride solid. So let's do that. In order to balance this, then obviously we have to put a 2 here and a 2 here to balance it out. But we could figure this out in a completely different way if we analyze it in terms of the oxidation process and the reduction process taking place. So this is an important part here to realize. Sodium loses 1 electron. And notice how we draw, or we write, the electron as a product. Sodium has lost it, so we have this perspective of the initial versus the final. So the initial system has only sodium, and the final has sodium plus an electron. Sodium has lost the electron. Chlorine, which is a gas, it's a diatomic gas, has to gain 2 electrons in order to form 2 Cl-. So here we have electrons being gained. So sodium is being oxidized and chlorine is being reduced. Now, if we were to combine these, we would notice then that actually this is providing 1 electron, but chlorine needs 2 electrons. And so we have not enough electrons to satisfy the chlorine, so this reaction will not go. So in order for there to be 2 electrons, we need to multiply the first reaction by 2. And if we rewrite this then, multiplying by 2, we get at the bottom here, we get 2 sodium on this side. We draw a line down the middle here, plus Cl2 plus 2 electrons makes 2 sodium ions plus 2 electrons plus 2 Cl-. The ultimate goal of any redox reaction that is balanced has to be that the electrons on both sides are the same, because you can't lose electrons that aren't gained by something else. Redox reactions are always coupled. There's always something being reduced, and there's always something being oxidized. This is the way they work. So the electrons, since they're on both sides of the reaction in equal amounts, they cancel. And we get then a chemical reaction that looks like the one we just started with, which is then 2Na plus Cl2 makes 2NaCl, where we know that this is then Na plus Cl minus as such. So this is the kind of conceptual thing that we have to work with now. So let's move on to a little bit more complicated material. So when we talk about oxidation and reduction, we have to introduce this concept called the oxidation number. And the oxidation number or oxidation state, these are equivalent statements, these being the same thing. So you have an oxidation number or oxidation state. This is what we can call the internal charge of an atom in a compound. So it's the distribution of charges within one. And for many compounds, for example with sodium chloride, it's really easy to see because we know that the sodium is plus and we know the chlorine is minus. But it's harder when dealing with a molecule like CO2. And so we have some basic rules here. We know, for example, that oxygen always forms O2 minus as an ion. Soda and fluorine, for example, always forms a minus ion, and 1 minus. And chlorine, for example, always forms a Cl minus ion. And sodium always forms a Na plus ion. So we can follow the rules of the octet what we call octet rule followers to predict what the oxidation number is on an unknown, where we don't know what it is right off the bat. So for example here, we do not know what the oxidation number for carbon is. It's impossible to predict it using the periodic table, since carbon can be both +4, +2, -2, and -4. It has 4 possible oxidation states. It actually has even more than that, if we're going to be really clear about that. So, but on the other hand, since oxygen is an octet rule follower, we can say then with pretty good certainty that whatever oxygen is going to be 2 times -2. And since this whole compound, or this molecule in this case, has no charge whatsoever, we can put this equal to 0. And then we solve for the difference and find the value of x. So in this case then, x plus -4 is equal to 0. So x equals +4. So the oxidation number or oxidation state of carbon is +4. This can be indicated in lots of different ways, but it's quite common to do it like this with Roman numerals, although no one ever does it for carbon dioxide. But it can be handy in other cases. Let's do another example. Let's look at this fluorine, this compound of fluorine and sulfur, or sulfur and fluorine. we notice that fluorine is also an octet rule follower, but we don't know what sulfur is. So again, X plus minus 1 times 6, so 6 times minus 1, and the overall charge is 0, so this is equal to 0. X minus 6 equals 0. X is equal to plus 6. So the oxidation number on sulfur is plus 6. We do one more example. Let's look at NO3 minus. So now the overall is not equal to 0, it's equal to minus 1. And the X is going to be plus, remember oxygen is an octet rule follower, so we have 3 times minus 2 equals negative 1. So X plus minus 6 equals negative 1. X is equal to plus 5. So the oxidation number for nitrogen is plus 5. In general, then, we can say something like this one. If you lose electrons, right, you have an oxidation. And you can also say then that the oxidation number increases. And this is an important point. So let's look at an example here in general. Here we have a metal M that is oxidized and becomes M+, just like sodium in our previous example. Obviously, the oxidation number in this case has gone from 0 to plus 1. So we have an oxidation number increase. That's oxidation, right? On the other hand, if you have a non-metal, like chlorine, that goes plus 2 electrons, we could do it with another example too, to Cl minus, then you have an oxidation number decrease, because the chlorine has gone from 0 to minus 1. Sorry, to minus 1. So if you have an oxidation number decrease, it's a reduction. And this has some important consequences that we'll just talk about just briefly for a second. So when we look at the rest of the problems that we're going to deal with today, remember this, that if the oxidation number increases, then it's an oxidation. If the oxidation number decreases, then it's a reduction. Let's look at a typical chemical reaction that we've worked with before. We have CH4 plus O2 makes CO2 plus H2O. Now, if we balance this correctly, we know that we have two of these and we have two of those in order to make sure that everything is balanced. And this is just a combustion. This is a combustion reaction. But all combustion reactions are a type of redox reaction. They're just a very specific type, so they're given a special name. If we look at this and we break it up into parts, we can break each aspect of it out. So let's look at the carbon first. So we're only looking at the carbon to begin with. So carbon is actually then going from carbon in methane to carbon in carbon dioxide. And if we look at the numbers here, we can see that if we calculate it properly, hydrogen is of course plus 1, and there's 4 of them. So in this case then, the oxidation number for carbon in methane is minus 4, according to this model. And if we go over to carbon dioxide, we see that we have 2 oxygens, so minus 4, carbon has to be plus 4. So the oxidation number has increased by 8. Which means that 8 electrons have moved around. And as I said before, if the oxidation number increases, then it's an oxidation. And an oxidation is a loss. So we can actually then determine that the direction of the electron flow is this direction. But where do those electrons go? So we have 8 electrons that have moved around. Then we have to look at the other part of this chemical reaction. And the other part is then the O2. So let's look at the O2 quickly. Here we have 2 O2. And where do the O2s go? The O2s go to CO2 and to H2O. And in the balanced chemical reaction, we see that there are 2 of those. So there are 2 H2Os. So here we have 4 times minus 2. Right? We have 2 here and 2 here. This is equal to minus 8. So the electrons then have gone from what? They've gone 2O2 plus 8 electrons give CO2 plus 2H2O. Because in the beginning, the oxygen, because it's bonded with itself, has an oxidation number of 0. But here, excuse me, here we have a total of 8 minus charges. So this is one way of explaining how combustions work. Now, what we're going to look at balancing chemical redox reactions in general. So sometimes when you balance a redox reaction, you actually don't know beforehand exactly how to balance it. We're going to do a really simple example to begin with and see that you can use what we call the half reaction method, which is similar to what I just did with methane. Let's look at an example here. Here we have cerium tin. So here we have cerium 4 plus and tin 2 minus. This comes from stannum, just so you know, which is an old Latin word for tin. So the overall reaction that we want to balance is then between cerium 4 plus and tin 2 plus. That turns into cerium 3 plus and tin 4 plus. If we break the two into two parts, then we can take this and see what happens to it. Sn2 plus becomes Sn4 plus. How many electrons have to be exchanged? Well, since we know that electrons have a negative charge, they have to be added to the side that where they end up. So in order for there to be a oxidation number increase, there has to be a loss of electrons. So you have to lose them on the product side, and we know that this is an oxidation because there's been an oxidation number increase. On the other hand, if we look at cerium 4 plus and it goes to cerium 3 plus, we can see that there's been an oxidation number decrease. So right away we know it's a reduction. So we know it has to be an electron gain, right? So the electrons have to go on this side. And since the difference in charge is only 1, we know that it's 1 electron. But in order to balance the entire reaction, the number of electrons on each side have to be the same. So we need to multiply this by 2 so that the number of electrons being produced on each side is correct. And we'll do this by then multiplying through, and we'll do it right away. So we can see then that this is going to be Sn2 plus, if we divide it down the middle, plus 2 electrons plus 2 cerium 4 plus makes Sn4 plus 2 electrons plus Ce3 plus 2. When we cancel the electrons, we get the balanced chemical reaction, which is then Sn2 plus 2 Ce4 plus makes Sn4 plus 2 Ce3 plus. And that's our balanced chemical reaction using a half reaction method. And this works fine for a lot of different chemical reactions where you can actually see the different components. But there are other times when you have to also consider the solution where the reaction is taking place. So sometimes the solution is important. And the solution can either be acidic, basic, or neutral. And if it's an acidic, that means that there are H plus extra. And if it's basic, that means that there are OH minus extra. And if it's neutral, it means that there's H2O. But in fact, all of them have H2O. So let's look at a chemical reaction where we have to take into account the different whether the reaction is acidic, basic, or neutral. So I'm going to balance the chemical reaction between permanganate and oxalic acid. Now, permanganate actually comes as KMNO4. But potassium is considered a spectator because it doesn't really participate in the chemical reaction. So we don't have to take it into account. It's basically a placeholder for a positive charge. So we're going to only regard the ion MnO4 minus. And we're going to react it with H2C2O4, which is oxalic acid. And it reacts to form manganese 2 plus ions plus carbon dioxide. Now, we can immediately recognize the fact that there are things that are missing over here, like H. Where is it? Because it's not showing up in this original. So it's an unbalanced chemical reaction where we're actually missing some of the products. And this is very typical for a unbalanced redox reaction in a solution. You'll find that that's the case. So the first thing that we want to do when we do this type of problem is we want to figure out what's being oxidized and what's being reduced. So we take it and we divide it into two parts. We have manganese here, we have manganese there. We take our MnO4 minus and we divide it into this half reaction. That's why it's called the half reaction method. And we realize, okay, so what happened here? Is manganese being oxidized or is it being reduced? And in order to figure that out, we have to go in and look at this as we did earlier and recognize that this is going to be minus 8. X minus 8 is equal to minus 1. So the oxidation number on manganese is plus 7. And the oxidation number on manganese ion here is plus 2. So using our earlier way of approaching this problem, we realize that there's something like 5 electrons moving around here. We also know then that since the oxidation number went down, that this is a reduction. Because the oxidation number went from plus 7 to plus 2. Then technically we don't really need to figure out what's going on in the second one, but we'll do it for practice anyway. Here we have oxalic acid, H2C2O4, plus CO2 makes CO2. In this case, it is an oxidation. And we know this if we look at it by quickly doing the calculation. We can say that this is plus 2, because it's hydrogen, it always makes a plus, right? And then we have plus 2x plus minus 8. And if we do the calculation, then 2x become minus 6 equals 0. And so x equals plus 3. And on this side we have x plus minus 4. So x equals 0. X equals plus 4. So the oxidation number has increased. Therefore, it's an oxidation. right away we can see that we need to balance the carbons, because up here we have one manganese and one manganese. So one of our first step is then to balance what we can see. And so we balance the CO2 with a 2. So now we have how many oxygens? We have 1, 2, 3, 4, and we have 4. And we have 2 carbons. So now we need to look at our hydrogens, and we can see, aha, the hydrogens are out of balance. And again, here's our problem. How are we going to solve this hydrogen problem? So, in order to do that, we have to make some assumptions. So I'm going to rewrite this chemical reaction down here. And we're going to deal with the first one first, the manganese first. In order to balance the oxygens that are missing on this side of the chemical reaction, we balance it using water. So in this case, we have how many oxygens? We have 4, so we need 4 H2O. Now the oxygens are balanced, but we now have the problem with the hydrogen again. We have 4 hydrogens over here, or 4 waters, so we have a total of 8 hydrogens. This means that we have to place 8 H plus on the other side. In order to make this work, on the other hand, though, we have to have an equal number of charges on each side. And since we already know that this is a reduction, and reduction is gain, the electrons are going to end up on the right-hand side of this reaction, because on the left-hand side of this reaction. But we can calculate this by looking at it. We can see that there's how many charges are here. We've got plus 8 minus 1, and over here we have plus 2. So we actually have then, if we cancel those, we have plus 7, and 7 needs to go down to plus 2. So how many electrons do we need to go from 7 to 2? We need plus 5 electrons. And if we recall from the up here, we can see that, yes, indeed, that can be predicted by the oxidation numbers at the very outset of our problem. Now, let's move on to the second part. In the second half of this reaction, oxalic acid turns into carbon dioxide, and we have 2. Now, if we were to look at the number of electrons involved in this, we would think it was 1. But it's going to involve 2. We can predict that using the oxidation numbers. But let's prove it using this method. So let's see here now. The carbon and the carbons are balanced, the oxygens are balanced, so we do not need to include water. The only thing that we need to include then is for the hydrogens, we need to put in 2H plus. And we can see then that since everything else is neutral inside of this reaction, then all the plus signs have to be balanced out by 2 electrons, which is predicted by up there. Now we can see that there's no charge over here, and the total charge over here is 0 as well. So on both sides there's an equal number of charges. Notice also that the electrons always end up on the same side of the chemical reaction as the H pluses. We now need to perform the act of making sure that the electrons in both of these half reactions are the same in number. And we can see here that we have 5 here and 2 here, and the lowest common multiple between the two is actually then 10. So this reaction has to be multiplied by 5. And this whole reaction needs to be multiplied by 2 in order to get 10 electrons on both sides of the reaction. So I'm going to move this paper up a little bit so we can see it more clearly. I'm going to write the whole thing out. So we take these two and now we add them together and multiply through. So 2 times 5 electrons is 10 electrons. 2 times 8 hydrogens becomes 16H plus. 2 times MnO4 equals 2 times MnO4 minus. And then we're done with that side for the first reaction. Then we have plus 5 H2C2O4. And then we go to the other side of the reaction. We have 2 times Mn2 plus 8 H2O. And then we take these. This is going to be 10 CO2 plus 10 H plus 10 electrons. So we almost ran out of room there. Now we cancel those things that are on both sides of the chemical reaction. And we notice right away that the electrons cancel, and that's the whole point. The whole point of doing this is to make sure that the electrons on both sides are the same, because the electrons that are gained here have to be lost here somehow. We have 10 hydrogens over here. All of them disappear, but we end up with 6H plus over here. Nothing else cancels in this chemical reaction, but sometimes you have waters that need to be canceled in some cases. So we end up with this reaction. So the reaction looks like this. 6H plus 2 MnO4 minus plus 5 H2C2O4 plus makes 2 MnO2 plus 8 H2O plus 10 CO2. This is a balanced redox in acid. Okay. So that concludes the video for this, or the instructional part of this video. I'm going to give you an additional one to work on. So what I want you to do is I want you to work and try to balance the following chemical reaction. Let's do this one. Fe2 plus Cr2 O7 2 minus makes Fe3 plus chromium 3 plus. So try this one out. And I can give you a little hint. The oxidation number of iron has increased. So that should be a hint on how to solve this particular problem.